Hello everyone, my name is Kyung-Nam Kang and I am a PhD student at Inha University in South Korea. The subject of my presentation is identification of external loads acting on the tunnel lining. The number and length of all tunnels are increasing worldwide, and accordingly, many cases of damage to the lining are reported. It is known that there are various causes of damage to linings, such as changes in the groundwater level and excavation in adjacent areas. However, since it is very difficult to design in consideration of these various causes, there are many cases where problems occur like the design. Fake analysis have been studied to solve these problems. The forward analysis is a method to obtain results such as displacement, stress, and strain from mechanical properties obtained through ground investigation after modeling the object to be analyzed. But the back analysis proposed by Sakurai is a method to obtain mechanical parameters from measurement data such as displacement, stress, and strain. So my research object is presented a back analysis algorithm that can find the magnitude and location of the external load acting on the tunnel. So the algorithm combines the beam spring model, which is one of the structural analysis methods for calculating the stress and displacement of the tunnel, and the differential evolution algorithm for back analysis. In addition, a scaled model test was performed to test the performance of the algorithm. The beam spring model is one of the structural analysis methods such as the elastic equation method and finite element method and finite difference method. In the beam spring model, the tunnel lining is expressed by beam elements and the ground by spring elements. A stiffness matrix can be constructed according to the stiffness formula of each element, and a global stiffness matrix can be constructed by the superposition principle. After that, the displacement and member force at each node can be calculated by the matrix product of the inverse matrix of the stiffness matrix and the force matrix. According to the Japan Society of Civil Engineers, the beam spring model can be composed of 6 types as shown in the figure below. The first is a model with constant rigidity without considering the joint of the lining. And the second is to use the equivalent rigidity for the rigidity considering the joint. The third is to use a hinge for the joint part of the lining. And the fourth model is to use a rotation spring instead of the hinge. The fifth and sixth models are models for considering the shear stiffness between the two rings, and there is a difference in whether the rings are rigidly or a shear spring is used. In this study, the second equivalent stiffness model was used. The differential evolution algorithm proposed by Stone and Price is designed to optimize nonlinear and non-differentiable continuous spatial functions and is a search technique using group-sized object variable spectra. The differential evolution algorithm is one of the evolution algorithms similar to the genetic algorithm, randomly generates initial objects and extracts suitable objects through mutation crossover, and selection. In this figure, G denotes generation in evolution process, D denotes dimension vectors, and P is the population size. F is the mutation constant with values between 0 and 2, and CR is the crossover constant with a value between 0 and 1. For each variable vector in a population, a new generation vector is expressed in equation 1. The new generation vector is called the crossover vector, which is generated from 3 different vectors and is chosen randomly. In the crossover stage, the parent vector is crossed with the mutation vector to generate a trial vector as shown in equation 2. Rand means the randomly selected change vector, and irand is a random integer within 1, 2. The back analysis algorithm combines the above two methods. The beam spring model and the differential evolution algorithm is shown in this figure. First, the diameter of the tunnel, the number of beams to split the linings, and ground condition are defined. Second, a local stiffness matrix is constructed through the stiffness equations of the beam elements and spring elements, and nodal force matrix is created as a ground condition. Third, each local stiffness matrix of the beam and spring elements is superposed, and the local coordinate is converted to a global coordinate by calculating the direction cosine matrix. Next, the stiffness matrix replaced by the global coordinate system is configured as a global stiffness matrix according to the principle of superposition. And displacement and member force are calculated through the nodal force matrix. And here, the difference between the calculated displacement by beam spring model and the measured displacement is defined and calculated as a fitness function. If the difference between the two values is greater than the predetermined error rate, the back analysis is performed through the differential evolution algorithm. The differential evolution algorithm calculates the fitness of each entity through the beam spring model for initial randomly generated target variables. After this, individuals with good fitness are left, and the rest are improved to have good fitness through mutation, crossover, and selection process, and this process is repeated as many as the predefined maximum number of iterations. This page is about a scale model test to verify the algorithm I just mentioned. The conceptual diagram of the model test for algorithm performance test is shown in this figure. External load is applied to the outside of scaled lining model with an outer diameter of 45.5 cm and a thickness of 1.5 cm using 8 hydraulic pressures, and convergence is measured through the LVDT inside. In the test, a load of about 0.25 kN is applied to simulate the isotropic state. After that, it was performed by applying additional external load of 0.2 kilonewtons to the 7 hydraulic pressure. At this time, the initial convergence was 0.02 mm on average, but increased to 0.32 mm at the 7th position by an external load. The input properties for the algorithm performance test are shown in the table. The modulus of elasticity and Poisson's ratio of the model were measured by performing a uniaxial compression test. In the model test, since there is no ground, it is correct to set the ground reaction stiffness to 0. But when the ground reaction stiffness is 0.001 kPa is used because the displacement is diverse in the beam spring model. The parameters of the differential evolution algorithm were defined as a rotation constant and crossover constant of 0.8. The number of population in one generation was 10, and the maximum number of iteration was 10. The value to be found through the back analysis was defined as the location where the additional external load was applied and the magnitude of the external load. Algorithm performance results are shown in this figure and table. In the model test, an external load of 0.452 kN was applied to the hydraulic pressure 7th, and an external load of 0.464 kN was applied to the hydraulic pressure 7th in the algorithm result. The location was accurately searched, and the external load was about 2.53% larger. The figure and the table and below table show the difference between the displacement calculated by the model test and the displacement calculated by the beam spring model. There is difference of about 0.1 mm overall, but the displacement of the 7th hydraulic pressure was 50% smaller than the back analysis result. This is judged to be due to the influence of the ground reaction stiffness, and the error rate is expected to decrease when actual field measurement data is used. So, the conclusion of this study is as follows. This study presents a back analysis algorithm to find out the magnitude and location of an external load to evaluate the stability of the tunnel to which the external load is applied. The algorithm was constructed by combining the beam spring model and the differential evolution algorithm, and the performance was verified by comparing the results of the scaled model test. The location where the external load was applied was accurately found, and the magnitude of the external load had an error of about 2.5%. So, the result of this study is a basic study for the back analysis of a tunnel in operation, where external loads are applied, and additional studies on other causes of compensation are planned in the future. If you have any questions, please send an email to the email address listed in the abstract. Thank you for your attention.